components. So the outline for my talk today is I'll talk a little bit about the different regions of geospace, the models that I'll be using, thermosphere mass coupling, other models that I'm using, and then electrodynamic coupling. So before we talk about geospace coupling or geospace modeling, the first thing you have to consider is the external drivers of geospace. So one of the biggest external drivers of geospace is the sun. So in this case, the sun is throwing out lots of vectors, and it's exactly, so the sun throws out a lot of vectors, mostly magnetic field vectors and velocity vectors. Occasionally they'll throw out scalars like density and temperature or radiation. This interacts with the geospace environment, and then it has all sorts of space weather consequences. And so it's a very important external driver. But in addition to external drivers, there are also a lot of internal processes that need to be considered. So in addition to those vectors, you have solar ionization. Solar ionization comes in, the radiation comes in, ionizes the neutral atmosphere, and gives us our ions and plasma and charged particles that form the ionosphere and everything above that, like the magnetosphere. All right, so that's just a quick introduction to external drivers to our geospace model. So now let's go over and talk about the models themselves. All right, so what is geospace? Geospace is an uncountable, it's a noun, it's uncountable. It's the region of outer space near Earth, including the upper atmosphere, ionosphere, and magnetosphere. I think they should probably add the lower atmosphere to this now going forward. And this is taken from the Wiktionary. I've never heard of that before. So the different regions of geospace is you have outer space with the magnetosphere way up above, and then the top. This row here is mostly the neutral atmosphere. So at the top of the neutral atmosphere you have the exosphere, followed by thermosphere, and then mesosphere, which kind of sits in between, and then a lot of the lower atmosphere, stratosphere, troposphere, and below. On the right side here is you have the ionosphere, which is the ion component, as opposed to the neutral component, and then above that, going all the way up through into the magnetosphere. So the ionosphere overlaps with the thermosphere and the exosphere. Exosphere modeling is pretty difficult, so as far as what I'm talking about and discussing today, it's mostly the thermosphere, ionosphere, and the magnetosphere. In the future, we'll consider lower atmosphere, the importance of lower atmosphere. However, right now we're just considering the thermosphere, ionosphere, and magnetosphere coupling. So when coupled together, they create this very complex chain of events. All of these internal processes are very complex and they span different scale sizes and grid sizes, the different structures, different physics. They're all quite different, and each one requires its own model. And so you have various models for each component within all of geospace. And then you have the external driver here, which generates your solar wind and EUV radiation. So this is quite complex. So how do we model this? So I'll discuss the models now. So the first model is the model of the magnetosphere. This is our first model that interacts with the solar driving. So the magnetosphere model here is the Lyon-Fetter-Morbury model, which is a global 3D magnetohydrodynamic magnetosphere simulation or model. It has an 8th order numerical reconstruction scheme. It also has a multi-fluid capability. So instead of treating the surrounding plasma as a single fluid, you can give it different species, different mass, each with its own momentum and energy equation. So the nice thing about this model is that with an 8th order numerical reconstruction scheme, you don't have as much numerical diffusion, you don't have as many inaccuracies as other models, you don't need as coarse of a grid as other models as well, or lower order reconstruction schemes. It's able to maintain waveforms really well, especially over long distances. It's also on a stretched spherical grid. This stretched spherical grid gives us all of the dense gridding near regions of that we're interested in. So the sun, for this particular plot here, the sun is on the right, and that comes in and then interacts with the front boundary here creating our bow shock, and then the rest of the magnetosphere. So Earth is at this point in the center here. You can see that most of our grid spacing is near Earth. So we don't have to go into a Cartesian grid where you would have very dense grid in regions that we don't care about. So this saves a lot on computation time. And with the high order numerical reconstruction scheme, we're able to capture a lot of interesting effects. For example, substorms, bursting bulk flows. We're also able to get a lot of very good Poynting flux specification. And then an output for the model is all of the MHD parameters like magnetic field vector, velocity vector, temperature over the entire three-dimensional space. It's really easy to use, very difficult to install. So we have a huge lack of users for LFM. And it's pretty simple. You only need two inputs. You need a solar wind input, and then you need a conductance. But the difficulty to install is that it has a lot of legacy codes and libraries. This model was created probably in the 1980s, early, maybe even 1980 itself. So it's a very old code, about 40 years now. So going a bit further in, we have the ionospheric boundary. So the model for this one is the magnetosphere ionosphere coupler. This is a really simple two-dimensional ionosphere shell that sits at about 100 kilometers altitude, and it solves the ionospheric potential using the field line current that it receives from the MHD. So it just simply solves the Poisson equation. In addition, it can take the MHD parameters and then using an empirical specification, it can calculate the precipitating energy flux and mean energy, which is very important for the ionosphere and thermosphere. The resolution for this one, it has pretty good resolution. So it can go up to about half a degree in latitude and longitude. And it gives us about 5-second time resolution, which is a lot better, which is a lot finer time resolution than a lot of the ionosphere thermosphere model. It provides dynamic convection pattern, dynamic global precipitation, and especially good monoenergetic and diffuse electron precipitation. It also provides us other precipitating electron populations, for example, the soft precipitation, in particular the broadband electrons and direct entry cusp electrons, which are very important for F region dynamics. So the other model is the ionosphere thermosphere model. I also have this misspelled. It should be TIEGCM as opposed to TEI here, which is the thermosphere ionosphere electrodynamic general circulation model. It's a bit of a mouthful. This is an open source community model. Everybody at NCAR knows about it. It's very lightweight. It's been the ionosphere thermosphere workhorse model for many years prior to WACOM-X. And then the high resolution version, which goes down to 0.625 and 1.25 degrees in latitude and longitude, this high resolution version isn't necessarily publicly available yet, but with the high resolution, it gives us very nice tongue of ionizations. For example, what you see here, we're able to maintain this tongue feature across the polar cap very nicely. However, if you go down to something like 5 degrees, which is what our older lower resolution version was, then this feature would be a single grid point and not very well maintained. So now that I've introduced the three important models for the magnetosphere, ionosphere, thermosphere, let's couple them together. So the history of the coupled magnetosphere, ionosphere, thermosphere, or CMIT, depending on who you talk to. So in 2003, the Ridley et al. Coupled Batsaras to time GCM using this scheme here. So what they took from time GCM is the MHD magnetosphere provides the particle precipitation pattern as well as the potential pattern to time GCM. Time GCM uses that for its dynamics. It gets its field line current, neutral wind driven field line current, and then it passes that current over to the MHD to solve for the potential. However, the conductance that they're using is still an empirical specified conductance rather than the conductance provided by the ionosphere thermosphere. What they found with using this neutral wind generated current system is that they found a 6% increase in the polar cap potential. That's not a very large contribution. So their conclusion was that the ionosphere thermosphere was not too important, and as far as I know, no further work from their side has continued along this line. In 2001, Rader et al. Coupled the UCLA magnetosphere model with CTIM, and the way they coupled it is they coupled both the neutral wind-driven fuel line current as well as the conductance. So through this slightly more complex coupling scheme, what they found was that the model produces more realistic electrodynamic and ionospheric response. So it was their conclusion was that it was a pretty significant improvement. Now we move on to the NCAR side of things. So from NCAR, Wenbin and Mike, so Wenbin Wang and Mike Wiltberger in 2004 wrote a pair of papers in which they coupled LFM to Ting. So Ting is the precursor to tiny GCM, where they coupled just the conductance. So unlike the Batsaras Ridley et al. Coupling, where they coupled the fuel line, the neutral wind-driven fuel line currents, and different from the Rader et al., where they coupled both the conductance and the currents. The only thing they coupled here is the conductance. Mike Wiltberger looked at the magnetosphere side of things, and Wenbin Wang looked at the ionosphere thermosphere side of things. So the way that it works is that LFM would provide the fuel line currents to the magnetosphere ionosphere coupler. The coupler solves for the potential and passes the potential to LFM. It also passes the potential and precipitating electrons to Ting. Ting provides the conductance back to the coupler. So this way, this is how you couple in the conductance here. So what they found was that from the magnetosphere side of things, the magnetosphere is not dramatically altered by the coupling. Although you do get more realistic conductances and much more realistic EUV distribution. So the standalone LFM on the left here, that you can see the conductance pattern here. So this was, state-of-the-art plotting routines back in 2004. So you can see the Hall and Pedersen conductance here. You can see it's just straight lines going across, and then you can see it looks drastically different from the CMIT or the Ting-provided conductance values here. Although both the potential and fuel line current patterns didn't seem to change too much, the Pedersen and Hall conductance are quite different. So it's important to note that this version that they're using had very low resolution LFM and very low resolution ionosphere thermosphere. On the ionosphere thermosphere side of things, the simulated response showed a significantly different response in the thermosphere ionosphere. So the potentials coming in, so this dashed line is the LFM potential versus the empirically specified potential pattern, which is this more like a step function here. So you can see that the potentials going in are quite different, as well as the precipitating flux is quite different. So they found a different response in thermosphere ionosphere. All right, so moving forward in time, we've added a new and better ionosphere model known as the Ionosphere Polar Wind Model, or IPWM. This is specifically an 8-moment, it solves the 8-moment equation for the major species. It is a high latitude ionosphere model. So it goes from the pole down to about 60 degrees latitude. It's a much more complex ion transport code than tiny GCM, and it extends an altitude range much larger than tiny GCM. So tiny GCM spans mostly about 97 kilometers up to between 600 to 800 kilometers, depending on the solar driving. And then IPWM in this case extends up to 8,000 kilometers. So it extends much, much higher than what tiny GCM does. The inner boundary of LFM sits at about 1 RE or so about 6,400 kilometers, and that's well within the realm of IPWM. So because it simulates the transport all the way up to the magnetospheric inner boundary, it's able to pass the ions from the ionosphere directly into the magnetosphere, also known as ion outflow. In addition to just simply simulating the transport, it also has this unique transversely accelerated ion specification using an empirical wave-particle interaction model, or in this case, I'll just refer to this as the WPI. So the WPI is regulated entirely by the AC pointing flux coming from the magnetosphere. So the AC pointing flux is you take the time average of the pointing flux, and then you remove the time average, and you only look at the fluctuation within the pointing flux. So using that, also known as S parallel in this case, you can see that the WPI electric field is a function of S parallel, as well as the WPI minimum altitude in which it takes place is also a function of S parallel. So it's used entirely to regulate this wave particle interaction model. So when we couple that in, so this is the four models we get. I've been calling the LFM, IPWM, TIGCM, or the LIT model. You get this complex coupling scheme. So with from the thermosphere, the TIGCM here, TIGCM provides the conductance to mix and the multifluid LFM, because we now have a ion outflow coming out from the IPWM. So with IPWM sitting here, we're now able to take TIGCM information, the neutral information from TIGCM, the thermosphere, and pass that to IPWM. IPWM then makes use of that to simulate the ionosphere and then pass that to LFM. So from the thermosphere point of view, the thermosphere used to only have one pathway to reach LFM, which was through this conductance arrow. Now with IPWM coupled in, it now has this additional pathway where it goes from thermosphere, IPWM into LFM. So this is an important new pathway that it can influence the magnetosphere, where the thermosphere can influence the magnetosphere. But because of this existing pathway, coupling this whole thing together, it's very hard to tease out exactly how important this new pathway is. So that's what I'll be talking about. Is we're going to isolate this new mass coupling because I'm calling it a mass coupling because what we're doing is we're passing the additional mass from the ionosphere to LFM. So this thermosphere mass coupling, the way to isolate that is we just simply close off this conductance pathway. So rather than TIGCM providing the conductance to mix, we're just going to have mix provide its own conductance. Therefore, the only way for the thermosphere to influence the magnetosphere is through this new arrow, through this new pathway. So the only way it can do that is it'll pass all the neutral density, temperature, and winds to IPWM. IPWM makes use of that to provide outflow into LFM. So we'll see how that interacts and how important that is. So the way we close that coupling pathway is by setting the F107 or the conductance in mix to be the same for two different runs. IPWM receives the same F10.7. So F10.7 here, the solar flux units, is used for both the solar ionization rate or the amount of photoionization in IPWM, in addition to the conductance. So we did two runs where the F107 in TIGCM differs. So we set it to 80 SFU as well as 230 SFU. So this corresponds to solar minimum and a solar maximum condition, respectively. So TIGCM's F107 is varied, however, everything else is the same. So what you see on the right side here is the Pedersen conductance used by mix as well as the Hall conductance used by mix for both runs. So there's no precipitation, it's just a very static conductance. So we have no feedback at all through the conductance. So we simulated a storm, which is this particular storm here, which is it's March 27, 2003. But because of the way we want to simplify everything, we set all of the asymmetric parameters, such as the velocity in the y direction, velocity in the z direction, bx and by, to be 0. So the only thing that's influencing our magnetosphere is the bz, the z component of the magnetic field, the solar wind density, as well as the vx, the velocity along the sun-Earth line here. We also used a slightly lower resolution than our maximum resolution, which is a 2-degree lat-long grid for the mix and LFM. TIGCM is 1.25 degrees, and IPWM is also 2 degrees. Okay, so what does the different thermospheres look like? So the top row here is the ADF thermosphere. The bottom row here is the 230F thermosphere. So if you take a look at the geopotential height near the top boundary of TIGCM, you can see that the max, all of the top, the altitude here ranges from about 480 kilometers to 540 kilometers. However, in the solar maximum, you can see the thermosphere is much more inflated, and you have from 600 kilometers up to about 740 kilometers. So you have a much more inflated thermosphere. Looking at the field line neutral wind quantities, you can see that the colors are much darker. Although the distributions are similar between the two runs, the colors are much darker in the solar minimum case. So at 400 kilometers, the field line neutral wind velocities are much larger in the solar minimum than in the solar maximum. As far as O2N2 ratio, which you can see that you have lower O2N2 ratio in the ADF run, and then you have more O2N2 ratio in the 230F run. Having a larger O2N2 ratio means that you have more O, more neutral O. With more neutral O, you're going to get more chemistry happening, and more chemistry means that you have more ions being produced, more especially O+ ions being produced. So that's given to IPWM, and then IPWM provides O+ ions into the magnetosphere. So let's see what happens to the lump system parameters. So these are large integrated system parameters. So the O+ flux is this top panel here. So in the 230F run, which is this blue line, you can see that the O+ flux is clearly greater than the O+ flux in the ADF run. Similarly, in the cross-polar cap potential, you see a tiny difference. You see the red being greater than the blue here. So if you have more outflow, you load more mass in the magnetosphere, you slow everything down, therefore you slightly reduce the reconnection rate as well as the cross-polar cap potential. But it doesn't change by that much. This is only upwards of 10% difference. And you can see that the largest difference is this 20 kilovolts difference as opposed to, but that's at the peak here. So that's about a 10% difference at most. So it's a very little difference in terms of integrated system quantities. If we split that up, instead of using a single number across the entire polar cap, we take a look at what's happening on the day side versus what's happening on the night side. You can see that in terms of the O+ flux, for the ADF day side number, you can see that the O+ flux is less than the day side number. And similarly for the night side, you can see that the O+ flux is less than the O+ flux for the 230F. And it's a 60% change as opposed to a 36% change. So changing the thermosphere seems to be impacting the night side fluxes a lot more than it's impacting the day side fluxes. But in general, you are seeing a difference in terms of the fluxes. If you take a look at the velocity of the O+ coming into the magnetosphere, you can see that on the day side, the fluxes or the velocities between the two runs are similar. They're both about 33 kilometers per second. And that has to do with the Poynting flux coming in. Because the solar wind driving between the two runs is the same, the amount of Poynting flux on the day side is also similarly the same. And therefore, you have similar energizations and therefore similar velocities coming out. But because you have a more inflated thermosphere during solar maximum, you get more O+ flux coming in. If we take a look at the night side, you can see that now the night side, you have very different velocities. You have much faster O+ velocities for the solar minimum case than you do in the solar maximum case. And that has to do with just more Poynting flux. So again, if you have more mass in the magnetosphere, then the magnetosphere, it has more inertia and it generates less, it's less able to generate Poynting flux. If you have less mass, it's able to react faster and generate much larger Poynting fluxes. So if we go back down to the ionosphere, we can take a look at the distributions. As opposed to taking a look at integrated quantities, we'll take a look at the distribution. So here, this top panel here is the ADF run. This is the polar cap potential distribution. This is the O+ flux distribution. You can see that as far as the polar cap potential, it's about the same. So this is averaged over this, I didn't mention it, but that's averaged over this yellow region here, which is near the maximum activity, just to emphasize the difference between the runs. So you can see that as far as the polar cap potential between the minimum and maximums here, they're pretty similar to each other. If you take a look at the O plus flux, you can see that the O plus flux in the 230F case here is much larger than the O plus flux in the 80F case. You can also see that there seems to be a significant dawn-dust asymmetry between the dust side on the left and then the dawn side on the right. So you can see that there seems to be this significant dawn-dust asymmetry. However, if you take a look at the O plus flux, you can see that on the day side, you have more fluxes coming out on the dawn as opposed to more flux coming out on the dust side. This asymmetry in the day side outflow is seen in observation. Keep in mind that we don't have any VY or BY in our simulation. So what is the cause of this? So typically if you have a BY or VY, you would, those are external forces that would cause some asymmetry in between the dawn and dust side. However, we don't have that in our simulation. So what exactly is causing this asymmetry here? So we took a look at a lot of different sources for what are the potential sources for what for causing this downward bias in the O plus outflow. So taking a look at the neutrals, so I've marked two diamonds on the figure here, and you can see this diamond on the right side, I've been calling as the pre-noon diamond, and then the diamond on the left side here is the post-noon, with noon being at the top here. So if you take a look at the neutral quantities, so O, O2, and N2, the neutral densities on the left as a log density from 0 to 10, you can see that there's very little difference between the pre-noon and post-noon, although the pre-noon has a little bit less neutral density. So this can't be the cause of our increase in O plus flux. Similarly, if you take a look at the temperature, the neutral temperature, you do see that the pre-noon neutral temperature is less than the post-noon neutral temperature. So this is most likely not the cause either. If you take a look at the O plus density itself, you see that the O plus density has some difference all the way up to 2,000 kilometers. You can see that there is some difference. Note that this is a much smaller scale than the scale that you see in the neutral density. And so this difference at about 1,000 kilometers is a factor of 4 or so difference between the post and pre-noon. So you do see more O plus density. You also have much hotter O plus temperatures. So what's the reason for causing both a hotter O plus temperature as well as more O plus density? So if you take a look at the energization scheme, if you take a look at the pointing flux, you can see that the pointing flux has more pointing flux on the slightly more pointing flux in this pre-noon sector than you do in the post-noon, and similarly, you have more BBE precipitation or broadband electron precipitation in the pre-noon as opposed to the post-noon. So both of these, the pointing flux could lead to more energization, and the BBE flux could lead to more heating at the higher altitudes. So we just simply looked at the different sources. We didn't narrow down exactly what is the source of this pre and post-noon difference. We haven't narrowed it down to exactly what the source is, but it does exist and it seems to be consistent within the model. So going back to that dawn-dust asymmetry in the polar cap potential, once the outflow comes out into the magnetosphere, the polar cap potential generates an electric field, and then that electric field starts moving the ions in the magnetosphere. So if we had a uniform conductance pattern, which is this top left plot here, which is not what we're using in this case. If we had a uniform conductance pattern, then our polar cap potential would generate very symmetric polar cap potential between the dawn and the dusk. That generates a very even and symmetric magnetosphere shape. However, if you have some sort of gradient in the Hall conductance, similar to what you see on this right plot here, then you have this dawn-dust asymmetry. This is work by Bill Locko that was published in Science, and you can see that once you have this conductance gradient, the magnetotail also becomes slightly asymmetric in addition to the velocity within the magnetotail becomes asymmetric as well. So now how does that apply to our O plus coming in? So when the O plus enters the magnetosphere, this is a really complicated plot. So this plot is a YZ cut plane. So so this is in the equatorial plane, this is X and this is Y. So now if we picked an X value, so in this case, I picked an X of minus 15 and we made a cut. And then we looked at it in 2 dimensions along the Z and Y plane, with Z being up and down and then Y being left and right. You can see that the green arrows here is the E cross B vectors. So this is the E cross B force and the direction that the ion outflow would be moving. You can see that they all have this slight dustward, pointing to dust is on the left, slight dustward component to them. So there is a dustward bias in this E cross B vector. The color in the background is the O plus flux, so you can see where you have a significant amount of E cross B vectors, so a significant amount of E cross B flux. You also have a significant amount of O plus flux. And then this black boundary is the open-closed boundary. And so when you're on open field lines and in the magnetosheath, you experience a significant amount of E cross B force, and then you move towards the dusk. Once you reach the distant tail and you enter into the magnetosphere, you maintain that distribution. So this is the equatorial plane. So this is X in the left and right, and then Y is the up and down. So you can see that the density, which is the color map in the background here, that you can see there is some asymmetry in the density, with slight more density in the dust side, which is the bottom side here, as opposed to the dawn side, which is the top side. And that causes this white contour, which is a BZ equals 0 contour, that separates the magnetosphere from the magnetosheath and then the solar wind. So you can think of the white contour as the shape of the magnetosphere. So you can see that in the 80F run, there's a significant asymmetry in the magnetotail. However, in the 230F run, you can see that there's not as much of an asymmetry. There is still some asymmetry, but not as much. So there is a significant, so the 80F run, where we're only changing the thermosphere and having the thermosphere influence outflow, is creating this very significantly different shaped magnetosphere. So although the integrated quantities aren't that different, the shape of the magnetosphere and the distribution of the magnetosphere is quite different. So to sum up the mass coupling, the conductance gradient caused by EUV produces dawn dust asymmetry in both polar cap as well as within the magnetotail. And then the outflow has a downward bias that's seen in observation. And the thermosphere can profoundly impact the distribution and shape of the magnetosphere. So for example, reducing and enhancing the dawn dust asymmetry that we saw in the magnetotail. So similarly here, you can see that this is a very exaggerated asymmetry compared to what we were seeing before in the Laco paper. However, in the 230, you can see that there's less of an asymmetry than you would expect. And that just has to do with the distribution of the O plus. All right, so that's going through the mass coupling channel. So I'll talk a little bit about the new models I'll be using for the electrodynamic. So going back to the conductance coupling. So the new model that we have, so as I mentioned before, LFM is an old legacy code built in the 1980. So the new model we have is Gamera, which is a rewrite of LFM. And that's part of this large scheme called the Multi-Scale Atmosphere Geospace Environment Model, or the MAGE model. So the vision for MAGE, the vision for the Center for Geospace Storms, which is a NASA Drive Science Center, is to create this large, coupled, and complex model. What we currently have is this much smaller version, where we couple Gamera to, instead of mix, we now have remix, tied GCM instead of WACOM-X, and RCM, which is the ring currents. So similar to what we were seeing earlier, which is coupling a magnetosphere model to an ionospheric potential solver and tied GCM, we now have the inclusion of RCM, which is the ring current model. So the advantage of this rewrite to Gamera, the rewrite to LFM, is that Gamera is much more efficient than LFM. Running LFM at one of its higher resolutions are known as quad resolution. Quad resolution LFM runs somewhere between 1 to 4 or 1 to 9 simulation of real time. So it's a pretty slow code. Gamera's quad resolution runs at real time and faster. And then Gamera has also been pushed to hex res, which is approximately 4 times greater in every dimension compared to quad. And that gives us an ionospheric resolution of about 0.25 degrees or so. So this has pushed the scale of what we can do, and it's also much faster, and we're able to get a lot more science out of it because it's so much faster than LFM. It's a big improvement. So compared to what I was showing before, which was using a 2-degree remix, using a 2-degree mix resolution, I'll show results using the 1-degree remix and using Gamera instead of LFM. All right, so the electrodynamic coupling, going back to coupling with Gamera, or coupling between the magnetosphere, ionosphere, and thermosphere. This is a comparison between the old models, which is all these plots on the right, with our new MAGE model, which is this plot on the bottom left. This top left part is just Gamera plus the ring current, and then we add TiGCM in, so we have a much more realistic conductance in this bottom left plot. So in the top left plot with Gamera plus the ring current, we see that where the region 2 currents aren't as strong. Actually, I think I have this backwards. This is Gamera plus the TiGCM without the ring current. Adding the ring current in, you get much stronger region 2. But then having TiGCM coupled in, we have a much better resolution, much better distribution of our field line currents compared to some of the older models. So this panel here, Ampere, is the data. Weimar is an empirical specification used by TiGCM standalone. So if you're using TiGCM by itself, it would be given Weimar as its potential and field line current pattern, as opposed to what you would get from a magnetosphere model, for example, Gamera or LFM. So LFM, the old LFM is in this bottom left here. You can see it doesn't do that well compared to Ampere. However, if you compare what MAGE produces with Ampere, sorry, my microphone ran out of batteries. So you can see that we capture the all of the distribution from Ampere much better than the older generation of models. Okay, so but as Wenbin and Mike mentioned before, CMET, it produces much better, it makes a much larger impact in the ionosphere and thermosphere as opposed to the magnetosphere. So if we take a look at the neutral density in the thermosphere, which is what's being plotted here, the standalone TiGCM driven by Weimar is the red curve here. CHAMP, which is a satellite, a LEO satellite that measures the neutral density, that can measure the neutral density. You can see that when you compare TiGCM with CHAMP, we're missing a lot of these peaks here that CHAMP measures, a lot of these spikes that CHAMP sees that TiGCM just doesn't capture. And then you can see during this period here, TiGCM just produces a lot of things that CHAMP doesn't see. However, when we drive it with the fully coupled model, we capture a lot of these early spikes. We also get a lot of the morphology throughout this middle period. So even though we're not capturing it exactly in this middle period, more active period, we're able to get a lot of the spikes, a lot of the morphology, much better than the standalone Weimar. So if we focus a little bit more on this early period here, you can see that there are a lot of spikes that TiGCM just does not see at all. So what is the reason for the coupled model seeing these spikes, but the standalone model not being able to see these spikes? Okay, so this is a movie. Let's see. Does it play? Okay, so this is a movie of the neutral density with Champ and Gray satellites flying through it. The northern hemisphere is on the left and the southern hemisphere is on the right. One thing to note is that the scale is constantly changing, so you can see these nice waves that are coming out from the polar region. So you can see these waves coming out. These waves are known as the traveling atmospheric disturbances, or TADs. So you can see that as we start reaching and getting closer to this period here where we saw good agreement, you'll notice that Champ and Grace are flying straight through these TADs. So these spikes that we're able to capture in the model are these TADs generated at the right time in the right place for the satellites to fly across them. The interesting thing about neutral density is that in order to get the neutral density and TADs correct, you have to get a lot of things correct to actually match the neutral density. So that implies that our model is getting a lot of the distribution correct, a lot of the amplitudes correct, and therefore we're generating a lot of the waves on time with the correct speed and in the right place. So even if large system quantities like Joule heating and the cross-polar cap potential are similar between models, because if you take a look at an empirical specification, empirical specifications do pretty well in terms of capturing what is the large system quantities like polar cap potential. It does a pretty good job of giving you this is the polar cap potential at this moment in time. However, the distribution is very different from what our model is producing. So you can see this is a moment in time that matches up with this particular peak here. So you can see that the Weimar model is a very different distribution than what it's a much larger, more diffuse distribution than what our MAGE model is producing. You can see the difference plot on the right. It's just drastically different between the two. So even though the integrated quantities are very similar, the distributions are very different. And when we're moving our models to higher resolution, the distribution starts to matter a lot more, especially the small scale distributions. So if we take a closer look at the waves, so we're going to put Weimar and the standalone TiGCM aside for a little bit and take a look at the waves. This is a plot of the time derivative of the neutral density at 400 kilometers. So it's the time derivative of the plot that we were seeing, or the movie that we were seeing, all at a fixed longitude. So longitude of 0 is at the top, 90, 180, and 270. Noon, UT is at the bottom, so UT noon is this green line in the middle here. So that corresponds with the longitude 0 on the day side. And you can see that you get a lot of structure, a lot of wave structures and TAD structures at noon. And then if you take a look at the dust side, you can see a lot more active and a lot more small scale structures in the neutral density. You get, once you move towards the midnight, you start seeing a lot larger scale structures. You don't see a lot of these small scale structures. These are large, broad structures. And then similarly on the dawn side, you don't see as much on the northern hemisphere. However, in the dawn side, in the southern hemisphere, you see a lot of these really small scale structures here. And then the waves all cross. They don't all cross, but you can see that they also interfere. They cross each other and they interfere and produce interference patterns. So the nice thing about these is that the wave structures are about 1 or 2 grid points in width. And so you need a high resolution model in order to actually see these. If you use a lower resolution model, like 2.5 degrees, then these span 1 grid point or less. So in addition to looking at the neutral quantities, if you take a look at the ionosphere, so the total electron content, so the ions and electron, you can see a lot of structures as well. So in this case, you have less waves, so they're not as sensitive as the neutral density. You can see a lot of very interesting features here. If you look really closely, you might see secondary waves coming out from the main wave, the main wave here. In this case, on the day side, you don't see as much structure. However, on the night side, you see a significant amount of structure on the night side. On the night side, and then especially over on the dawn side. So if we zoom in a little bit, so I zoomed in between 12 and 16 UT just so that we can see some of the structures. I've also added some lines to see the propagation of the waves. So you can see that from this plot up here, if you take a look at this line, you can see that once at the early period here, the line is moving pretty straight. Once it interferes, you can see that the line has started deviating from this straight line. So once it interferes, you can see that it changes velocity. But prior to interfering, you can see that it maintains its velocity. Similarly, if you take a look at the other time periods, you can see that before it interferes, it has a constant velocity, and once it interferes, it changes velocity and changes velocity here. So you can see it deviate from what it was doing before, and that seems to be pretty consistent across all of these. I've also circled all of the interesting small-scale structures. So in this case, you can see in the northern hemisphere a significant amount of small-scale structures that don't travel very far in terms of latitude. So similarly here in the southern hemisphere, you can see that a lot of small-scale structures that once you move towards the equator in the middle, they start to disappear. In the TEC on the right, you can see that an interesting thing about the TEC is that when the waves interfere, they actually seem to be enhanced. So you get this enhancement after they interfere, and then prior to interfering, you can see that they're relatively weak. And so interfering seems to pick up larger amplitude waves, and maybe a slight slowdown in their velocity, similar to the neutral density over here. But the main point is that you see them picking up amplitude. Additionally, in the dawn side, you can see that there seems to be these. So blue is a decrease in the TEC. You can see there seems to be these decreases in TEC that spawns from these interference location that are at a 45-degree angle from or less than 45-degree angle, but they're at an angle from the interference, or from the propagation of the two waves. And so I'm really unsure what exactly is happening to generate a lot of these. So this high-resolution simulation seems to produce a lot more questions than it does answers, but you do see a lot of very interesting effects that we can start to dive into with the high-resolution simulation. So high-resolution modeling, empirical specifications are no longer enough. You need high-resolution models. You need good distribution, and you need a coupled model to give you all the right distribution in the right at the right time, at the right location. And then northern southern hemisphere responds very differently. So you also need to take care of the northern hemispheres equally. And then takeaways from the wave analysis is that you can see that the waves bend or change speed when they interfere with other waves, and then that seems to introduce a lot more questions than answers. Thank you.
Thanks, Kevin. Does anyone have any questions?
Hi, Kevin, this is Astrid. Maybe I can ask a naive question. So you showed these examples where TIDs are kind of crossed and interfered, and the velocity changed of the propagating one. Does this depend on the magnitude? So is the velocity changing more if the TID is stronger or so?
That doesn't seem to be the case, because if you compare this line, and this line, you can see that so this is the TAD, but you'll see similar curvature in the TEC, change in velocity in the TEC. So with the TAD, you can see that even though the amplitude here seems to be about the same as this amplitude, you can see it's curving a lot more than this one down here. So you can see this separation is a lot larger than this separation, and then similarly, this is a very small separation between these two waves interfering. You can see a much smaller separation. So it doesn't seem to be dependent on the amplitude of the waves interfering. It could be due to the latitude in which they're interfering. So if they're interfering a lower latitude, it could have additional. There could be additional dynamics occurring in the lower latitudes that's allowing them to curve more or less.
But what is shown here is the change in TC and in the density. So it's not the,
Yes, so it's the change in TEC and density. So you would expect a wave traveling to, and the wave amplitude traveling to be approximately close to the amount of change.
Kevin, this is Gang.
Hi, Gang.
Yeah, it's a very nice display for the display TID and TAD for in this manner. So what is the time? I assume are you saving the file every the DT is DT 5 minutes?
DT is 1 minute.
1 minute. Okay, I just wondering if you change the DT longer time, is the phase speed changes or not?
So when I tried that, the phase speed did not really change.
Okay.
It still looks very similar to what you see here when I did DT of 5 minutes. Because when you calculate the phase speed, you would calculate it per second, and so everything gets scaled anyways.
I see. So is this at the constant pressure level or constant height?
So the neutral density is at a constant height, while the TEC is the whole column. So.
Okay, that's right. Yeah.
So that might explain why you see a lot more structure in this plot here. When I show the full time series, you see a lot more structure than you do in the TEC, because TEC, a wave would have to move the entire column. So you have a lot more background. However, since I'm looking only at 400 kilometer, a single altitude, you see the wave structures much more easily.
Yeah, I see. So another thing is, I think that change of the phase speed property. I don't know whether the interaction will change the phase speed or not, but the phase speed definitely changes with local time. So it's not always a straight line because it's a local temperature. I'm sorry. So the phase speed is dependent on the local temperature. So it does not necessarily it's always straight line. Yeah.
That's good to know. Because since these are all at a constant longitude, as you move forward in time, they'll move to a different local time.
That's right. Yeah, but the latitude changes, so also temperature will change.
Yeah.
Hi, Kevin.
Hi, Wenbin.
Yeah, related to Gang's question, have you looked at the temperature, the TAD and temperature, neutral temperature, and the altitude profiles of those things?
So when I made, so I did the temperature with a similar plot to what you see here. It looks really similar to what the density shows.
Okay.
There wasn't as much difference. So especially if I scale this, instead of doing an absolute value, an absolute difference, if I did a percent difference between time steps, then the neutral density produces it correlates really well with the change in neutral temperature.
Okay, thank you.
I have Kevin's Bill Lutko. I have a question about the source of these perturbations. And if you could go to the plot that has both the neutral density and the TEC on the same chart, I think. Yeah, this one right here, dt by dt. I can't really. I mean, the lines are not as vivid in the TEC plot as the density plot, but it looks like in the density plot, the source is at relatively high latitude, maybe even in some cases very close to the pole, depending on the longitude you're at. Whereas in the TEC plots, it looks to me like the source, in other words, where those lines emanate from early in time, is happening at much lower latitude for TEC than for neutral density. Am I interpreting this right?
That's a good question. I don't know the answer to that. I haven't looked at how they're generated yet. So presumably you could have a TAD first, and then if you have additional heating as it's traveling, then you would generate the TEC, or not TEC, but TID that is correlated with it, but they're not always correlated with each other.
Yeah, I wouldn't necessarily think they would be correlated. I mean, there may be something that, you know, does that, but it's just I just, if I'm interpreting what I'm seeing in these plots, it just seems like the latitude and therefore the source of the neutral density waves, TADs, is occurring in a very different location than the TIDs, which is, I mean, curious. I'm not challenging anything here. I'm just trying to interpret what I'm seeing.
I think that's a good question. I don't know the answer to that. I haven't looked at the source generation of these yet.
Okay.
Kevin, I have a question. So in the earlier plot where you showed the model results in comparison with the two satellites, you know, show very general agreement.
Yeah.
Yeah, this one. So not this one, the next one. Yeah, here. So I saw that the places where they do not agree, maybe not always, but sometimes they do not agree, are at the place where the peaks, observed peaks, are really sharp. Do you see? Do you look at the reason why they don't agree? Is that because it's really a very small scale structure, so that it just missed? I mean, this one is still okay, but maybe later there are some peaks that maybe yeah. For example, the really big one.
Yeah. So
kind of yeah. Go ahead.
I've tried looking at this before, and what I seem to find is that at the cusp, if these fly really close to the cusp, they seem to be missing. The model seems to be missing heating. So we don't have all the heating that should be in the cusp. So that's what it seems to indicate. So this right now is a CME storm, and we get pretty good agreement. But in a CIR storm, where you have a lot more pointing flux and a lot more energy going into the cusp, the agreement is much, much worse.
So you don't have cusp precipitation in the simulation yet, right?
Right. So this simulation does not have cusp precipitation, and this simulation does not have alphanic heating in the cusp. And so if you notice, Grace is sitting right here. The cusp is a little bit polar of that a little bit. It's about here, but the Grace is flying through really close to the cusp, and it's missing. You know, we've completely missed the spike here.
So increasing resolution in the future may not address this. You still have to.
We would still need to. Right. We would still need to
heating.
include some additional physics.
Okay.
Or just include a cusp.
Yeah.
Yeah.
Mm-hmm.
There is cusp precipitation going into the IGCM, but it has to be populated with something.
So that's on our to-do list. So we do have cusp precipitation in the LFM model, but we don't have that with Gamera yet. We're still working on that.
Right. Because many of the later spikes are captured by the model rather well, I'd say.
Yeah.
Yeah, look at those. I mean, it's great.
Oops.
Mm-hmm.
Yeah, it looks like a model captured the low and mid latitudes TAD pretty well, but not in the cusp region. That's very interesting. So.
I see. Yeah, this one is pretty good.
Yeah, that's the champ one and the lower latitudes near the equator looks pretty well captured that one.
Yeah, so we're able to capture a lot of the waves that travel, you know, like Wenbin just said, near the equator. And then occasionally there are a lot of the waves that they look like they're near the equator, but they actually came from the opposing pole. And so they're traveling from South Pole to North Pole, and we're able to capture the full propagation of those as Champ and Grace fly through.
And the big peak around the 12 UT, which seems misses in both hemispheres. I'm sorry, not both hemispheres. These are two satellites. So that's also a cusp problem, you think?
Because the location they're at right now, they're flying towards the cusp here. I think we're missing an energy source that would have generated a wave, a TAD.
Okay.
So
right.
I think there's supposed to be a TAD there that we didn't generate because we're missing some sort of cusp region. So you can see that they're both flying straight towards that cusp.
Yeah.
Okay. I have another question. Earlier, you were showing in the first part of the discussion the coupling through mass, the outflow. You said that the experiment, the design, you have to cut the channel through the through the conduction. I don't understand, why couldn't you? I mean, if you keep this channel and run with or without IPWM, will that tell you the effect too? I mean, why do you have to cut the potential coupling?
So doing it that way, if you just do with and without IPWM, that starts to answer the question of what is the importance of outflow in general, as opposed to how does the thermosphere regulate outflow and how does the regulated outflow influence the magnetosphere. So if you cut out IPWM altogether, then you're comparing a run that has no outflow with a run that has outflow, as opposed to the experiment that we're doing right now, which is comparing two different thermospheres and how they control two different amounts of outflow, and how they control the characteristics of outflow.
I see. Okay. Thanks.
Okay, do we have any more questions? If not, then thanks for the talk, Kevin. And I think this is the last of our colloquia for this year. We have Thanksgiving, AGU, Christmas coming up, so we'll see everyone again in January.